So verifying is verifying at a point. Proving is proving over all the values. Okay, who am I over this side? You'll be here. Don't want to run. Okay, so some things about proving identities is we're really picky about the way you set them up. The nice thing about the exam is it will give you the T-chart to do the left-hand side, right-hand side, like Carson. It will be labeled left-hand side, right-hand side, so you should be okay. I put together the January 2017 exam for you guys. I just condensed it into a smaller document. Okay, so you can prove an identity by working both sides of the equation. Sometimes you only have to do one side. Sometimes you have to work both. So that you get it down so that the left-hand side of the equation equals the right-hand side of the equation. They look exactly alike. Like I said, you got to be very specific. I know in checks, I'm a little lazy, like it says 3 plus 1 equals 4. I don't go the next step and say 4 equals 4. In proofs, you have to. Okay? So in proofs, you have to get it so they look the exact same. You can't leave one side sine over cosine and the other side tan. You have to get it tan on one side, tan on the other. Does that make sense, everybody? You got to be specific. You're talking about something, right? Again, the format for solving identities, be sure not to forget things like angle variables in your expressions, because that is just, you're going to get deducted marks for that. So people say cotan sine, but it's really cotan theta, sine theta. So make sure those thetas translate all the way down. So what we're going to do is, do you have your format sheet in front of you? Because that's handy dandy. Formula sheets? Yes. Okay, so we're going to prove this. So again, we're not verifying. It's not for like we're saying it works at pi over 3. We're actually going to do this for all values of theta. So this is the hard part, Carson. This is the hard part. The hard part. So you're going to end up making a T-chart. This is Carson's hard part. And I understand, Carson, because I do it wrong as well. Left-hand side, right-hand side. You treat this line in the T-chart like it's the equal sign. You no longer need it. So you're going to rewrite cotan theta, sine theta, and on the right-hand side, cos theta. So in this situation, when I'm looking at this, really, cos theta is as small as I'm going to get it. So in this scenario, I'm only going to be working the left-hand side. Because I'm looking at this and there's nothing I can do to simplify it. But there is stuff I can do to simplify this. So what's cotan? Yeah. Cosine theta over sine theta times by sine theta. What are you going to do? Cancel out the signs. What are you left with? Okay, you can't leave it. You can't leave it at this step. You cannot leave it at this step. You have to finish it here. Okay? So you got to make it look pretty and clean. So cosine, cosine. So I'm going to say left-hand side equals right-hand side. And then my proof. It's my favorite part because it's a lot of problem solving and you get the hang of it. But if you're not going to practice it, it's not going to be get any easier for you. So if you're copying the identity answer to the back of the book and just throwing stuff on the page to fill it out, I know none of you would do that, but I can't show you, like I don't have the capabilities of showing you every possible proof over there. There's just too many. So if you want to get good at them, it's actually doing them that's going to make the difference. And yes, doing the hard ones. Like doing your 12 graphs. It's funny, you know, like I'll mark the tests before I mark the assignments. And then I kind of get like, did I teach it terrible? Did I miss something? And then I go mark the assignments and realize that nobody graphed anything and that I shouldn't be that upset that we didn't do well on the graphing part of the task because nobody practiced. All right, so I see on the left-hand side there's something I can do, and I see that there's stuff on the right-hand side I can do. So I'm going to work both sides. Okay. All right, I thought we were doing. All right. So sin x, cos x, and you told me this was cos x over sin x. You will be deducted a half mark if your question says x and you use theta. Kills me every time. I suck at that part. So what's going to happen here in this long line of stuff? The sines cancel each other out. And what's cos x times cos x? Cos squared x. Anybody recognize that?
Yes.
Yes. What is it? It is. What formula is it? It's the Pythagorean rearranged. So it's the first identity on your green sheet, but it's rearranged. Or sorry, I have this pink sheet. I'm looking at a green sheet. So this is cos squared x. Left-hand side equals right-hand side. I have done proofs that have taken up a whole page. Okay? So these are nice and simple and they're pretty obvious, and that's where we're starting, but you are going to get more complicated. But you're not going to get so complicated that they're unsolvable. How about this? I'll tell you this, any proof that we give you is going to work. So anytime on a provincial exam or on a test, if I say prove this identity, I'm giving you something that can be proved. That's true, but I've never seen it done. All right, double angle identities. So left-hand side, right-hand side. So on the provincial exam, they give you this T-chart. So they tell you the way if they want it to be done. Don't view from that. So I have tan x over 1 minus cos 2x over sine 2x. I can work both sides of this. Don't know if I want myself enough room. So this is going to be sine x over cos x. That's nice. I may end up putting that back to 10. I'm not sure. I don't know what's happening on this side. This is going to be 2 sine x cos x for my denominator. Now I just got to figure out what it is I'm trying to get rid of. Because cosine, the double angle cosine identity has 3 options. So, what's on the bottom over here? Cos x. What's on the bottom over here? Cos x. So I know I want to keep that. So what do I want to eliminate? The two sign X. So if I'm looking at my double angle identities for coast, which one would you anticipate me using? The one with just sign in it, because that's what I'm trying to eliminate, right? I'm trying to get sign off the bottom. If I use the one with cosine and sine, I'm going to end up eliminating cosine off the bottom, which is going to be complicated later. So I'm going to have 1 minus. That's what it is? No. There's 2 in there. There's 2. There we go. I'll just stick that in there. So I'm left with sine x, cos x. So these ones are going to end up canceling each other out. Subtract a negative 2 sine x. So I'm going to write that a little bit different. It's going to be 2 sine x times sine x all over 2 sine x cos x. Cancel out the 2's, cancel out the sines. What am I left with? So on the left-hand side, so proving identity takes tenacity. You know what I mean by that? You know what tenacity is? Like the ability to attempt something, fail at it, attempt again, keep going until you find success. So this is a really good example of somewhere where if you chose cosine, it's not going to get you to this answer. It's going to give you a simplified version, but it's not going to get it to match this one. So you have to go back and try it again. So people don't like identities because they don't want to waste time doing it wrong and fixing it. You guys don't have that time in your life. But when you get them, it's really fun to do. I'm not sure I know of any actual job that I would be proving identities, but there's lots of things you have to create equal scenarios. Right? There's lots of computer programming stuff where you have to create a program that mimics and gets the end result of this. Like often this is backwards design. Right? So I'm giving you this and I'm telling you it's gotta look like this and you gotta figure out how it looks like that. So it might not be that you're ever going to use identities ever again in your life, but the ability to backwards design, change the way something looks, and to any job, even mine. We look at where we want to be at the end of this, and then we build backwards. Like when we start. So although you probably won't be doing identities anywhere in your world, you will be doing tenacious things in your life, hopefully. All right. I think I want to hit pause. Oh, no, I don't want to hit pause. No, I don't want to hit pause. So you guys are like, oh, I'm going to cross all time and cancel these out, and then they're going to be equal to each other, and it's going to be great. But you can't do that with the proof. You don't keep the equal sign. You got to work the left-hand side and the right-hand side. Okay, so I have 1 minus cos x over sine x, and I have sine x over 1 plus cos x. So you're treating them as 2 different expressions. Treating them as 2 different expressions. So sometimes, like when I look at this, I'm like, oh, that's a Pythagorean identity, just for your range. But it's not. I think it is, but what is it missing? The square. So there's nothing I can simplify here. There's a couple of things I can do. I think maybe my heart might go to, okay, This is 1 over sine x minus cos x over sine x, so that would be cosecant, don't write this down, over cotan x. Don't write it down. It's not wrong, it's a simplified version. But if I do it on this side, still, don't write this down. Oh, yeah. How's that working out? Anything match? Still the same. Still the same. And if I go down here, well, I remember seeing a cosecant. Well, but it's cosecant squared identity. So that's not helpful at all. So although I simplified it or changed the way it looks, I haven't proven that identity. So this is the tenacious part. Sometimes we try stuff and it doesn't work. So try it with a pencil or an erasable pen. Get rid of it because we're going to do something else. Pretty good started band. Okay. This looks like an identity. I'm going to make it an identity. So you guys have 1/2. I need an equivalent fraction of the denominator of 36, right? So Kevin, mathematically speaking, what did you do to 1/2 to get it to look like that? Okay, multiply top and bottom right through. That's going back to your, I don't know where we simplify fractions, maybe equivalent fractions. We've done that before, we're going to do it here. So I'm looking at this, what would I need to multiply it by to get it to equal 1 minus cos squared theta? This is your difference of squares knowledge. Difference of squares. If I multiply them, I'm going to get 1 minus cos squared theta. And here's the thing, if I do it to the top, I have to do it to the bottom. Do I have to do it to the other side? No, because this is an expression. Expression, this is your rational functions coming back in. If you have an expression, it's top and bottom. Okay? We no longer have that equal sign, it's gone away. So if I multiply this out, this is going to be 1 minus cos squared x. And I'm not going to multiply. No, I'm not going to multiply. What's that simplified to? Sine squared. What should I do to simplify? That sign is going to cancel out the squared, right? So is this going to mess anybody up if I do it like that instead of rewriting it? So I'm going to be left with sine x over 1 plus cos x. That look familiar? That's the right answer. So I need to make the statement left-hand side equals right-hand side. So we tried something at first, it didn't work. It looked like an identity, it wasn't an identity, but you can multiply things top and bottom. You don't have to do that to both sides. You have to do it top and bottom. This, yes. Anytime you multiply something in, anytime you see the thing that you're supposed to multiply in, that's the next level. Like these ones here, like page 1 stuff, really, this is a 1 mark, 2 mark at most identity. you might want to multiply both by 10 to get rid of the denominator. Now we're going to get more complicated where we have fractions inside of fractions.
Yes.
Thank you. All right, I think I just saw this. Didn't I just make that? I think I did. Okay, so cotan x minus cosecant x equals, no, not an equals. I can say, don't use equal sign. Never done a 2 before I write down cos. Cos 2x minus cos x all over sine 2x plus sine. Okay, I must forewarn you, gut reaction is common factor, right? Does that work? No? Maybe not? No? Harrison didn't have that same feeling. You can't common factor. This isn't cos squared. This is a double angle identity. So there's only one cosine. So you can't take it out. You can't take cosine x. You got to replace the identity with something. So question of the hour is, what do we replace it with? That cos 2x gets you every time because there's 3 options. Suggestions? Let's try one. Pick one. Like, there's no notes in front of me. I didn't teach this last period, so I can't remember what I'm doing. So let's try something. Okay, let's try that one. So we're going to have cos squared x minus sine squared x minus cos x. That's my numerator. All over, this one I only got one option. So 2 sine x cos x plus sine x. Can I cancel stuff out? These are all separated by subtraction signs on the numerator. This whole denominator would have to go in here. This whole denominator would have to go into the middle term, and this whole denominator would have to go into the end term. That looks ugly. Nope. Because this whole denominator treated like a binomial. That would be like saying and you go, these twos cancel each other out. If you do that, okay. So don't do that because it's pretty terrible math. Don't do that. I'm looking at that numerator and it looks pretty terrible. Restart new formula. Yeah. What? I don't know, I haven't heard this one yet. That's the one that you have in there. We're trying to simplify this. Like right now, I got nothing to simplify this. That's it? Always. And then walk away, hope for the best. So maybe let's get rid of this. Let's try a different one. Try the cosine. Ooh, let's try the sine. 1 minus 2 sine squared x minus cos x. Okay. All right. So we have to on sheet 4. So this is going to be cos x over sine x subtract 1 over sine x. can simplify that even further to be cos x minus 1 over sine x. They have the same denominator. Really, we still like I can call it back to the sine x from the bottom. I think it is. What if? What if I change this? Again. Oh. You can't? It is getting somewhere. Do you see it? Awesome. All right. Well, at least you're honest. Does that look like something I might be able to factor? Right? Like if you think of this as 2x squared minus x minus 1, can you factor that? So that's going to be what an equal angle factor. So this work I would show anywhere on my identity proof. I would do this on a scrap piece of paper. I wouldn't do anything with it. But really what I'm looking at here is 2 cos x plus 1 times cos x minus 1 all over sine x times 2 cos x plus 1. So it took me 3 attempts. Looking at it, it just didn't look right. There wasn't anything I could simplify. But this works. This cancels with this. I'm left with cos x minus 1 over sine x. So that factoring, and I are going to say that left-hand side equals right-hand side. That statement I was saying, like in grade 10, you need to know how to factor, you need to be able to do it quickly, you need to be able to see those things. Okay, quickly is like the least important thing we need to do. Efficiency for identities, that goes with the later. There's nothing efficient about identities when we have to work through a more complicated one. I'd say this one is more complicated than the one we have to multiply with. Okay, so it's all what you see.
That's for 0 when it works.
Really?
No, the first one we can get.
The first one you got.
No,
The first one is verified. You got that.
That's for 0.
Why? You don't want to attempt it? Awesome. Very. Okay. Sometimes things happen. This actually is a nice one. If you can see it. Okay. Do you want me to pause the video? So I've got sine 2x minus cos x over 4. I missed a variable. Sine squared x minus 1. Anybody fearful of that cube?
Yeah.
Don't be. It's gonna go away really quick. Okay, so obviously what I'm gonna do is I'm gonna sub in what I know here. So this is gonna be 2. When I look at this, does anybody see anything magical? It's a difference of squares.
I've seen it.
Seen it? Got it? Difference of squares. So those are things that like I've got a lot of practice doing, but some of you those things may not leap off the page at you right yet. But like I said, the only way you're gonna get better at this is if you can actually do them. I'm looking at this, and what I'm going to take out is a cosec. I'm going to common factor of a cosec. And we're left with 2 sine x minus 1 over 2 sine x plus 1. It is. It took some factoring. Not too much else I can do here. So I'm going to leave that there. Hey, look, denominators are the same. So, and then this one, although it looks really scary, it's got the cubed in it, and I don't really know what to do with the cubed. You guys haven't factored yet, so don't see the cube. Look, just common factor in a cos. There's a cos in this one, and there's 3 coses in this one. So if you take a single cos out, you're left with sine squared x plus cos squared x all over 2 sine x plus 1. Does anybody see anything? Anybody see? This compared to an identity, which is equal. 1.
Oh my gosh.
So left-hand side equals right-hand side. So I love identities for the fact that you eventually get to the same place. I hate identities because they're not efficient. I dislike the part of identities that I can't do it quickly, and sometimes it's not obvious to me that it jumps off the page. So that's the identities. That's my favorite. My favorite option in grade 12. Feels like one by too fast. I'm looking to go all new extra assignments on the